Hello and welcome to our presentation on the algorithm edit distance presented to you by Zabeen and Mohammed Farhadul. What is the edit distance or the Levenshtein distance? The Levenshtein distance between two words is the minimum number of single character edits required to change one word to another. It was named after the Soviet mathematician Vladimir Levenshtein, who considered this distance in 1965. This distance is a generic distance where you assign a cost to the operations insert, delete, and substitution over the strings. The Levenshtein distance is an instance of the edit distance where all the operations have a cost of 1. It may also be referred to as edit distance. Now let us consider a problem where there are two strings and we can perform the operations insert, remove, and replace on them, where all of them have a cost of 1. We must find the minimum number of edits required to change string 1 to string 2. In our first answer, we see that we have to change card to March. We can at first remove C, then insert M, then replace T with C, and then insert H. We have a cost of 4. However, this is not the desired output as it is not the minimum number of edits. Hence, we have to find the minimum number of edits based on the cost. Next, we see another answer where we only perform 3 operations, such as replacing C with M, replacing T with C, and inserting H to change cart to March. The output is 3 and hence the minimum cost is found. Now we have another solution, the brute force solution using recursion. The idea is to use all the characters one by one by starting from either left or right of the both strings. Let us traverse from the left corner. There are 2 possibilities for every pair of characters being traversed. M is the length of string 1 and N is the length of string 2. First, if the last 2 characters of the string are the same, we cannot do much. We must ignore the last characters and get account for the remaining things. So we consider and recur for the lengths M-1 and N-1. Second, the else condition. If the characters are not the same, if the last characters are not the same, we consider all operations on string 1. Consider all 3 operations on the last character of the first string recursively and compute the minimum cost for all 3 operations and take the minimum value. First, insert, recur for M and N-1 plus the cost of insertion. Second, remove, recur for M-1 and N plus cost of removal. Third, replace, recur for M-1 and N-1 plus the cost of replacing. Now let us take a look at the pseudocode of the edit distance algorithm. First of all, we take an input alpha and beta, where alpha has n characters and beta has n characters. We also take an input of the operation cost. There are 2 base cases here. If m is 0, then we return n. If n is 0, then we return m. Now we compare the last characters of the 2 strings, and if they're the same, then we ignore the last characters and get account for the remaining characters. Finally, if all the other if conditions fail, then we return the minimum operation costs that we have. Here, the first recursive call is for insertion. The second recursive call is for removal or deletion. The third recursive call is for replacement or substitution. Now let's look at the simulation for the recursive tree of edit distance algorithm. We have 2 strings, t and set, where we have to convert t to set. First, we do the remove operation where we remove t from the first string and we are left with EA and SET. Then we do the insert operation, we insert S from the second string and we are left with TEA and ET. And now we'll do the replace operation where we replace T with S and we are left with EA and ET. Now from the EA and SET, we will do the remove operation like before and we'll be left with A and SET. Then we will do the insert operation and we will have EA and ET. Then we will do the replace operation and we will have A and ET. Now from the TEA and ET, we will do the same 3 operations again. Remove, insert, and replace. Now from EA and ET, we see that the characters have matched. There is an E in both. So we don't do any operations for the characters and we are left with A and T. If we keep going, then we'll end up with a recursive tree just like this one. We can see that we ended up with multiple solution paths which are highlighted with the red circle, but looking at the levels, we'll easily figure out the minimum cost path here. This actually gets calculated in our program and we finally take the minimum one. Hence, the minimum path is shown, the minimum edit cost is 2, and the operations are highlighted with red circles. The steps are replacing T with S and replacing A with T. The cost is 1 each, and hence the minimum cost distance is 2. In time and space complexity, the time complexity is O 3 to the power n. Since at every comparison step we are making 3 choices, making it roughly big O 3 to the power n algorithm. For space complexity, it's big O m. Here m is the stack space of the recursion tree.
As you can see, there are subproblems which are being solved again and again. All the encircled nodes are called several times. For example, EA and ET are called 3 times, which are marked with green circles. Now, the dynamic programming properties. Since the subproblems are called again and again, this algorithm has overlapping subproblems and optimal substructure property. So, how will we follow the dynamic programming approach? We have to solve problem by combining solutions to subproblems. We'll initialize a 2-dimensional array where we will store the values of subproblems. We follow the bottom-up or the bottom-down approach to solve our problems. Here, we will be using the bottom-up approach. This is the pseudocode for edit distance algorithm which follows the dynamic programming approach. We take alpha and beta as inputs, where alpha has m characters and beta has n characters. We also take the operation costs as our inputs. First 2 for loops here are used for making the dynamic programming array, which stores the values of subproblems. Now, we use a nested loop to compare 2 strings. Here, these 2 if-else statements are used to compare null strings, which we'll see in the simulation. Now, this if statement means if the characters are the same, then we pick the diagonal cell's value. Here, d of I-1, j-1 is the diagonal cell. Now, in this else if condition, where the characters don't match, we take the minimum cost of operation from 3 operations. Finally, we end our loops, and the bottom right cell will have our desired output, which is d of mn. Now, the simulation. We create a 2-dimensional array to store the values of subproblems. In the top right corner, we will show the executed code or operation. Let us start filling when one of the string is empty. We will compare card to null and then march to null. To convert null to null, we need no operations, so we put 0. To convert CE to null, we need 1 operation of replacement, so we put 1. To convert CA to null, we need 2 operations, one of replacement, another insertion, so we put 2. If we look closely at our code, we will see it is automatically giving the numbers as these values have obvious results. So we get 3 and 4. So we get the values like this. And we do the same for March. Now C and M do not match. So we replace C with M and take the minimum value from the marked cells and add 1 to it. Here, the minimum value is the highlighted blue cell. So after getting the minimum, we add 1 to it and we get 1. The last characters of C and MA, which are C and A, do not match. So we had to replace before, now we insert A and take the minimum value of these 3 cells and add 1 to it, which is 2. Now C and the last character of MAR do not match, so the minimum operation plus 1 will be 3. Now C and the last character of MARC matches, so we take the diagonal value, which is 3. Now C and the last character of MARCH do not match, so minimum plus 1 will be 4. Now A and M do not match, so we take the minimum of these 3 cells plus 1, which is 2. Then A and A matches. We take the diagonal value, which is 1. Then A and R do not match. We take the minimum of these 3 cells plus 1, which is 2. If we keep going, we will get a table like this. Finally, we will return the bottom right corner or the last cell of the 2-dimensional array, which is 3, our desired output. Now let's talk about the time and space complexity of this method. As we can see, there's a nested loop in our pseudocode the time complexity is big O of m into n or big O of n squared, where m and n are the lengths of the strings. The space complexity is also big O of m into n or big O of n squared. As we create a two-dimensional array, we get such space complexity. Now, here's a comparison table of the naive approach versus the dynamic programming approach. We can see that dynamic programming approach is better in terms of time complexity. Now let's talk about some optimization. There's a space complex solution where we only create an array of 2 into string 1 length as we require the upper row only. Here, the space complexity is only big O of m or big O of n. One of the variants of edit distance algorithm is least common subsequence. LCS or least common subsequence is a variation of edit distance where we are allowed to do only 2 operations, such as insert and delete. Here, we have to find the edit distance in this variation. For example, if we have string 1 C, D, E, F, G, A, B, C and string 2 C, E, F, D, A, B, G, A, C, then our least common subsequence will be C, E, F, A, B, C and the length of it will be 6. Now, some applications of edit distance are natural language processing, where the algorithm is used for spelling correction, OCR correction, and to approximate string matching. And of course, computational biology. This algorithm can be used to quantify the similarity of DNA sequences. Other applications of this algorithm are plagiarism detection, remote screen update problem, and Apache Lucene, which is a search engine software library. So this is all from us. Here are some references and links. Thanks for watching.